welcome to this problem walkthrough. Today, we'll be exploring problem number 2018, titled Check if word can be placed in crossword. In this challenge, we'll analyze how to determine if a given word can be positioned within a crossword grid while adhering to specific placement rules. Let's dive in and break it down step by step. In this problem, you are given a crossword puzzle represented as a 2D grid called board. Each cell in this grid can either be an empty space, denoted by a space character, a blocked cell indicated by hashtag, or a lowercase English letter. Additionally, you are given a string word, which consists of lowercase English letters. Your task is to determine if the given word can be placed onto the board either horizontally or vertically. The placement can occur in four possible directions: left to right, right to left, top to bottom, or bottom to top. To achieve this, the word must fit entirely into empty cells or match existing letters on the board. However, the word cannot overlap with any blocked cells or mismatch any pre-existing letters. The function should return true if the word can be placed on the board successfully and false otherwise. Let's consider a specific example to understand the problem better. Here, the board is a 3x3 grid where certain cells are blocked, represented by hashtag. The empty cells are shown as spaces, and there is one cell containing the letter C. The word to be placed is ABC. In this case, the output is false. This is because the word ABC cannot fit on the board either horizontally or vertically. There is no sequence of three consecutive empty cells or matching letters in any row or column that would allow the entire word to fit. Now, in another example, the board has a different configuration. Here, the board contains a mix of empty spaces, blocked cells, and some letters. The word to be placed is again ABC. This time, the output is true. The word ABC can fit vertically in the second column of the board, starting from the top. The cells in that column contain the letters A, B, and C, matching the word exactly. This demonstrates how the word can align with existing letters on the board, as long as the placement meets the conditions specified. In the next example, we have a simpler scenario where the board consists entirely of blocked cells except for a single empty space in each row and column. The word to be placed is just the single letter A. The output in this case is true. The word A can fit into any of the empty cells, either horizontally or vertically. Since the word is only one character long, it does not require consecutive empty cells, making it easy to place. Finally, it is important to note that matching the word with the board can occur in any of the four directions: left to right, right to left, top to bottom, or bottom to top. However, the placement must ensure that no part of the word overlaps with any blocked cells, indicated by hashtag. Similarly, if the word overlaps with existing letters on the board, those letters must match exactly. This requirement ensures that all placements are valid and adhere to the constraints of the problem. To solve the problem of checking whether a word can be placed in a crossword puzzle, we need to evaluate the grid in both horizontal and vertical directions. The brute force approach is the simplest method to consider. Here, we examine every possible starting position on the board and attempt to fit the word both forward and backward in each direction. For every attempt, we check two conditions: first, whether the word aligns with the empty cells or matches any pre-filled letters, and second, whether the placement is valid, ensuring it fits within the grid and is properly bounded by blocks or edges. However, this approach has a significant downside. Its complexity, M*N*K, grows quickly with larger grids or longer words, and it doesn't optimize for scenarios where blocked cells could help reduce the search space. This inefficiency makes it impractical for larger inputs. A more efficient alternative is the optimized directional search. Instead of blindly testing all positions, we first identify valid slots in the grid where the word could potentially fit. This involves scanning the board row by row and column by column to locate sequences of contiguous empty cells or pre-filled cells matching the word. Once we have these slots, we refine our search by validating their length, ensuring they match the word, and confirming they are appropriately bounded by blocks or grid edges. Finally, we check if the word can be placed in each slot, either forward or backward. This method is far more efficient, with a complexity of M*N plus K*S, where S is the number of valid slots. By focusing only on these slots, we eliminate redundant checks and significantly improve performance, especially in sparse grids with many blocked cells. The chosen strategy for this problem is the optimized directional search. The key idea here is that the number of valid slots in the grid is much smaller than the total positions, particularly in grids with many blocked cells. By narrowing our focus to only these valid slots, we reduce the search space and make the solution more efficient. A valid slot must be the same length as the word and bounded correctly by blocks or edges. To simplify implementation, we can handle both forward and backward placements by simply reversing the word. This approach leverages the grid structure to prune invalid positions early, achieving significant performance gains. While optimized search is slightly more complex to implement than brute force, it scales much better for larger grids. This makes it the preferred approach, striking a balance between clarity and computational efficiency. In this problem, we are tasked with determining if a given word can be placed into a crossword puzzle grid, which is represented as a 2D array. Each cell in the grid contains either a hashtag to denote a blocked cell or a blank space. To place the word in the grid, several conditions must be fulfilled. First, the word must fit exactly into the available blank spaces. Second, it cannot overlap with any blocked cells. Finally, if there are pre-existing characters in the grid, the word must align properly with those characters. To solve this, we'll follow a structured approach. We begin by parsing the input, ensuring the grid and word are in the correct format. This initial step helps prepare the data for the subsequent checks. Once input parsing is complete, we proceed to evaluate potential placements in the grid, starting with horizontal placement and then moving to vertical placement, systematically checking each possibility for validity. Now, let's focus on checking horizontal placements. The process begins by iterating over each row in the grid. For every row, we traverse through the cells to identify consecutive blank spaces, which we call blank segments. As we traverse, we keep track of the start and end indices of these segments. Each blank segment is then validated against two conditions. The first condition is that the length of the segment must exactly match the length of the word. If the segment is shorter or longer, it cannot accommodate the word. The second condition ensures there are no conflicts between the word and any existing characters in the segment. Specifically, if a segment contains a non-blank character, it must match the corresponding character in the word. If both conditions are satisfied for any segment, the word can be placed, and we immediately return true, terminating further checks. Next, we evaluate vertical placements using a similar approach. Instead of rows, we iterate over each column in the grid. For each column, we traverse through the cells to find blank segments, just as we did for rows. As we identify these segments, we track their start and end indices. Each blank segment in a column is then tested against the same two conditions. First, the segment's length must match the word's length exactly, otherwise, it is disregarded. Second, we confirm there are no conflicts between the word and the segment. A conflict occurs if a non-blank character in the segment doesn't match the corresponding character in the word. If both conditions are satisfied for any vertical segment, we return true, indicating a valid placement. If neither horizontal nor vertical placement is valid, we return false to signify that the word cannot be placed in the grid. The key insights of this algorithm lie in its systematic approach to evaluating both horizontal and vertical placements. By scanning the grid row by row and column by column, we ensure that every potential placement is considered, and no valid option is missed. The validation process, which checks segment length and character alignment, guarantees that the word is placed without violating the constraints of the puzzle. The separation of horizontal and vertical checks simplifies the logic, making the algorithm easier to implement and debug. The algorithm leverages a 2D grid structure to represent the puzzle, while the word is handled as a simple string. Index variables are used to track the start and end positions of segments during traversal. From a complexity perspective, the algorithm operates in O(m*n) time, where m is the number of rows and n is the number of columns, as each cell in the grid is visited once. Space complexity remains O(1), since no additional data structures are required beyond basic variables. There are several edge cases to consider to ensure the algorithm is robust. For instance, if the word's length exceeds the dimensions of the grid, it's immediately impossible to place the word, and we can return false. Similarly, if the grid is entirely filled with blocked cells, there are no valid spaces for placement. Another important case is when the word needs to align with pre-existing characters in the grid, which must be carefully verified during character alignment checks. Special scenarios, like an empty word or an empty grid, also need explicit handling to avoid errors. Additionally, the algorithm must handle situations where there are multiple valid placements, ensuring it identifies the first valid option and exits early for efficiency. To optimize further, we use techniques like early exits, skipping segment validation if the length is mismatched, and minimizing unnecessary character comparisons by focusing only on non-blank cells. These optimizations ensure the algorithm performs well even in larger grids. Here, we start by defining a class called solution and a function within it named canPlaceWord in Crossword. This function takes two inputs, board, which represents the crossword grid, and word, the string we are trying to fit into the grid. Inside this function, we define another helper function called canPlace, which checks if a given word can fit into a specific line of the crossword. The logic in canPlace begins by calculating the lengths of the word and the line, and then iterating through possible starting positions in the line. For each starting position, we first check if the word is bordered by empty spaces or hashtag symbols to ensure proper placement. If that condition is satisfied, we then use a nested loop to verify if each character in the word matches the corresponding character in the line, allowing for blank spaces to act as wildcards. If a match is found, the function returns true. Otherwise, it continues checking until all possibilities are exhausted. Next, we define another helper function called check, which iterates through each row of the board and uses canPlace to determine if the word can fit in any of the rows. If it finds a valid placement, it returns true. Lastly, we create a reversed version of the word using slicing, as this will be useful for checking placements in both original and reversed orientations. Now, we handle the case where the word might fit in columns instead of rows. To achieve this, we transpose the board using Python's zip function, which effectively converts columns into rows. With the transposed board, we can reuse the same check function to see if the word or its reversed version can be placed in any of the columns. Finally, the function combines all possible checks using a single return statement. It evaluates whether the word or its reversed version can fit in the rows, or in the columns of the transposed board. If any of these checks succeed, the function returns true, indicating that the word can be placed in the crossword. Otherwise, it returns false. This approach ensures that we efficiently check all possible placements of the word, covering both rows and columns in both forward and reversed orientations. Here, we begin by defining the core structure of our solution. In the canPlaceWord in Crossword method, we take the crossword board and the word as inputs. First, we create a reversed version of the word, which allows us to check for placements in both the forward and backward directions. The method then evaluates four scenarios: placing the word in the rows of the board, placing the reversed word in the rows, and the same two checks for the transposed version of the board, which represents the columns. This is achieved using a helper method check to encapsulate the logic for verifying word placement in a particular orientation. The check method iterates through each row of the provided board and calls another helper method, canPlace, to determine if the word can fit within that specific row. By combining these checks, we ensure all possibilities are covered for valid placement, whether horizontally or vertically, and in either direction. The canPlace method starts by iterating through the given row to determine if the word can fit starting at any valid position. It considers the word's length and ensures that the placement won't conflict with boundaries or pre-existing characters. The condition here checks if the position where we want to place the word is surrounded by obstacles, such as the character hashtag, which blocks placement. If this condition fails, we move to the next position. Then, for each potential starting position, we verify character by character whether the word matches the current segment of the row. If any character conflicts, meaning the cell either isn't a blank space or doesn't already match the word's character, the match is invalidated, and we break out of the loop. However, if all characters align, we confirm that the word can indeed be placed and return true. If no valid match is found after checking all possible positions, the method ultimately returns false, indicating the word cannot fit in this row. Finally, we define the transpose method, which is essential for checking word placements in columns. Transposing a matrix involves flipping it over its diagonal, effectively converting rows into columns and vice versa. To achieve this, we initialize a new 2D array where the number of rows and columns are swapped. Using nested loops, we iterate through each cell of the original board and map its value to the corresponding cell in the transposed matrix. This allows us to create a column-wise representation of the board that can be processed using the same logic we use for rows. Once the transposition is complete, the resulting matrix is returned. This method ensures that our solution remains efficient and avoids duplicating logic for handling rows and columns separately. To solve this problem, we need to determine whether the word can be placed in the crossword, either horizontally or vertically. In this first example, the board consists of 3 rows, and the word we are trying to place is cat. We start by considering the reversed word, which is tack. Then, we check each row for a valid placement of the original word. In the first row, the segment is not a match for cat, so we move to the second row. Here, the sequence T matches the word, so this row is valid for placement. Since we found a valid placement, we can stop further checks and return the result. Now that we've confirmed a valid placement, the function returns true for this example. Let's consider another scenario where no match exists. Here, the word is dog, and the board consists of 3 rows. We begin by reversing the word to get God. Checking the rows, the first row does not contain a segment that matches dog. Similarly, the second and third rows are also checked, but no valid segment matches the word. Since no placement is found in the rows, we proceed to transpose the board, which means flipping it to check columns as if they were rows. The transposed board now presents the columns as rows, but even here, no valid segment matches dog or God. As a result, we determine that no valid placement exists for this word. In this case, after checking both the rows and the transposed columns, no valid placement is found for the word dog. Thus, the function concludes and returns false. Now, let's explore an example where the word matches vertically in a column. The board has 3 rows, and this time the word is cat. First, we reverse the word to get tack. Checking each row for the original word, none of the rows contain a valid placement. Since no matches are found in the rows, we transpose the board. Transposing the board flips the rows and columns, so the columns become rows for the purpose of checking. The transposed board shows that the second column contains the sequence T, which matches the word cat. This column is a valid placement for the word. The canPlace function identifies this match and confirms that the word can be placed vertically in the board. Since a match is found in the transposed columns, there is no need to continue further checks. This placement is sufficient to determine the result. With a valid placement identified in the transposed board, the function concludes and returns true for this example. This demonstrates that the solution is able to check both rows and columns effectively by transposing the board when necessary. By handling both the original word and its reverse, we ensure that the word can be placed in any orientation allowed by the rules of the crossword. This completes the walkthrough of how the solution works across different scenarios. To analyze the time complexity of the solution, we start by breaking down the operations. First, reversing the word allows us to check placements in both directions. If the word has a length of n, reversing it takes n time since every character must be processed. Next, when we transpose the board using the zip function, we are effectively converting rows into columns. For a board with a rows and C columns, each row contributes C to the operation, and there are rows. This results in a total time complexity of C for the transposition. Now, when we check rows and transposed rows, we rely on the check function. Within check, the canPlace function is used to determine if the word can fit. The outer loop in canPlace iterates from 0 to mn, where m is the length of the row or column and n is the length of the word. This leads to mn plus 1 iterations. For each iteration, the inner loop compares a substring of length n with the word, which requires n time. Combining the outer and inner loops, the total complexity of canPlace is m*n. Since the check function calls canPlace for each row, its time complexity for the original board is r*m*n, whereas the number of rows and m is the number of columns. Similarly, for the transposed board, the time complexity becomes c*r*n, as there are C rows, originally columns, and each has r elements. Combining these, the overall time complexity of the solution is r*m*n plus c*r*n. Simplifying further, we get O, R asterisk C asterisk N, where the dominant term depends on the larger of R and C. Moving on to space complexity, the solution requires additional memory for specific operations. Reversing the word creates a new string, which uses O, N, space. Transposing the board generates a new representation with dimensions CXR, contributing O, R asterisk C, to the space complexity. The functions check and canPlace use only local variables and input arguments, so their contribution is constant, or O1. The total space complexity of the solution is dominated by the transposed board, which requires O, R asterisk C, space. Adding this to the space needed for reversing the word, the overall space complexity remains O, R asterisk C. Comparing this to a brute force approach, it becomes clear how the optimized solution improves efficiency. In a brute force method, we would check every possible placement of the word on the board, considering all starting points and directions. For a board of size xc and a word of length n, this would involve O, R asterisk C asterisk N, placements, with each placement requiring O, N, operations. The resulting time complexity would be O, R times C times N squared, which is significantly less efficient. The optimized approach avoids redundant checks by leveraging row-wise and column-wise traversal, coupled with early termination in the canPlace function. This reduces the time complexity to O, R asterisk C asterisk N, a substantial improvement over the brute force method. Now, let's consider the best, average, and worst case scenarios for the algorithm. In the best case, the word can be placed in the very first row or column, allowing the algorithm to terminate early. Here, the time complexity is O, R asterisk N, for row traversal or O, C asterisk N, for column traversal, depending on where the word is found. On average, the algorithm checks a subset of rows and columns, leading to a time complexity closer to O, R asterisk C asterisk N. In the worst case, all rows and columns need to be checked in both directions, resulting in the full time complexity of O, R asterisk C asterisk N. In conclusion, the optimized solution achieves a balance between readability and efficiency. By utilizing early termination and matrix transposition, it minimizes redundant checks. While the space complexity is driven by the transposed board, the time complexity of O, R asterisk C asterisk N, makes this approach well suited for handling larger boards and longer words efficiently. When solving this problem, there are several common mistakes to watch out for. First, failing to check both horizontal and vertical directions is a frequent oversight. Crossword puzzles allow words to be placed in either direction, so ignoring one can lead to incomplete or incorrect solutions. For example, you might validate a word horizontally but miss a valid placement vertically. Next, edge cases can be another pitfall. Scenarios such as the word being the exact length of a row or column, or grids with fully filled rows, are often overlooked. These cases can reveal flaws in your logic that would otherwise go unnoticed. Lastly, not validating the cells surrounding the word placement is another common error. It's not enough to ensure the word fits in the intended space, you must also check that placing the word doesn't interfere with adjacent cells. This ensures compliance with crossword rules, which typically require that words don't disrupt other parts of the grid unnecessarily. Another mistake to avoid is assuming the grid is always perfectly sized. While many examples use rectangular grids, some problems may involve irregularly shaped grids or additional constraints, making input validation crucial. A common error is neglecting to account for these variations. Additionally, overcomplicating your solution can create more problems than it solves. Using excessive data structures or unnecessary loops can make your code harder to debug and slower to execute. Instead, aim for a straightforward approach that focuses on efficient grid traversal. From an interview perspective, it helps to recognize patterns in grid-based problems. Techniques like breadth-first search, depth-first search, and directional movement are widely applicable, so practicing these can build your intuition. Constraints also play a key role. Understanding grid size, word length, and other limits can help you optimize your solution. Finally, iteratively testing your code is invaluable. Start small, perhaps with a 2x2 grid, and gradually tackle more complex cases. Using helper functions for direction handling can also simplify your code, improve reusability, and reduce redundancy, making the overall solution cleaner. This problem is closely related to several others, such as LeetCode 79, Word Search, and LeetCode 212, Word Search 2, which also involve grid traversal and word placement. Problems like LeetCode 36 and 37, Valid Sudoku and Sudoku Solver, share similarities in terms of validating constraints within a grid structure. When considering alternative approaches, brute force is a straightforward option where you iterate through every cell and attempt to place the word in all valid directions. While simple to implement, this method can be inefficient, with a time complexity of n²k, where n is the grid size and k is the word length. A more optimized approach involves pre-computing valid placement areas for horizontal and vertical directions. This reduces redundant checks during execution but may require additional memory for pre-processing. Another strategy is using backtracking, where you attempt to place the word and recursively backtrack if it fails. This approach is beneficial in problems with multiple solutions but may be less efficient for simpler tasks focused on validation. Each method has its trade-offs, and the best choice depends on the specific problem constraints and requirements. Great job! In this session, we covered how to determine if a word can fit into a crossword grid, touching on algorithmic strategies and spatial reasoning. Remember the key takeaways, and keep practicing similar problems to sharpen your skills. Thank you for watching, and be sure to check back for more coding tutorials. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!